Good morning. Having problems with my Bluetooth headset today, so I'm going to be recording on the laptop. I'm going to try to stay in front of it so it's not so echoey. We're here to talk and review later today for the second exam, and all the materials in terms of the things that I promised last week are up there. I also have up at the front of the class just the raw paper from exam 1, which I want you to come up and just come up to the folder, and that way you'll have your cheat sheet back and your paper. There's no marking on it. I just want you to take it back. And for those of you that are watching the video, I will give this folder to Charant, who's going to be giving the exam next week, and you can at least claim it at the exam. The main advantage in having this, the papers back, is you get your cheat sheet back and your other printed crib sheet. So we'll be talking more about that later because I suspect other people are going to wander in, but right now we're at a low count of 3. So what's been going on? My son's wedding was very good. Unfortunately for some of my family, like my wife and my son who lives at home, they both are sick. We did too much socializing, I guess. So they're all threatening to say, are you going to get sick, and when are you going to get sick? And I'm traveling on Saturday morning, so I don't know. I'm hoping for the best, obviously, but all of that went well. I've pushed on many things just since Sunday afternoon I got back. So I did put up the solutions to set number 7. I've inventoried all of the homeworks. I have all of that accounted for those of you that turned it in or did not turn it in. I'm going to talk about Project 2, which is very close to getting posted. I'm just refining some of the writing, but we will talk about it today. So one of the things I want to also talk about, since it's still on my mind when I was driving down here, is I'm planning on trying to do a lecture at home. Probably Thursday is what I'm thinking of right now. And if there's something you've looked ahead at the new homeworks or anything that remains, even though it may be pushed out there, but something that you've particularly taken a look at already and would like to have me comment on, I will try to do that. If not, I'm going to do what I think is right to do given the allowance of time, because I do have to finish the project, I have to make the exam, I have to write the solutions for the exam in advance as well. So I still want to do something though, and if that doesn't work well or if that's not complete enough, it's going to be up to you to go and take a look at the old lecture video. So you're just going to be down in here, and you're going to be looking at any of these lecture videos, probably not the last 2 because we're going to be talking about those on the last day of class, but anything you want to look at will be here, and if I get a chance I'm going to look into them, but I can't watch all those lecture videos either while I'm still prepping stuff, but they're there. And if I add anything, you will see after today, you'll see a lecture 12, and then if there's anything else I write up, it'll show up in the lecture videos, and I'll let you know about it in Slack as well. So the important dates has not changed. We're still running on the exact same setup that I wrote for last week. So what's up next is on this Friday, I want the papers turned in by noon, and I'm going to post the solutions for those, so those at least will be out there. I'm leaving on Saturday morning, like I've said already, and then the next thing up is exam 2, which will take place a week from today at 9:15, and Charant is giving the exam. Everybody in here, except for one person, knows him because he runs the lab, so he's going to do that. So look forward to that. I mean, look forward to that in the sense that, yeah, you don't want to have to take the exam, but you want to process through to the end of the semester. So that is going to be happening. One project has been turned in already. I'm hopeful that everybody else will get it in even earlier. What I'll be doing while I'm gone in terms of logging things in and sort of acknowledging it on my tablet to myself for record keeping. I can't say how that's all going to pan out. Tuesday the 28th is what we're talking about for the any lecture I might write, and it will probably it'll just apply to finishing off the semester. But I don't anticipate I'll be able to do 2 complete lectures. Don't really know. We'll return to class, set number 9 is due on Friday, May 1st, and that's just trying to keep you marching along. I'm feeling very crazy about all of this. I'm feeling somewhat betrayed by Dr. Trimboli, who said, we'll take care of it, because just keep in mind, I didn't sign up for this class not knowing I was going on a trip. I said, I can't do this when he asked me. And then he said, we'll take care of this. And I interpreted take care of this as I'll have somebody to hand the class off to you. But at any rate, it is what it is. We have to suck it up, basically. I'll be back on the 5th, unless something happens with my airline travel. And then set number 10 is due on that Friday. There's even some hints for set number 10, which are actually embedded in the solutions to one of the sample exams I just posted. Now, most of you aren't going to be able to maybe connect the dots on that. I am going to point it out at some time today to at least say, hey, be smart, and I'm hopeful that you will at least see that when you're studying for the exam, and you'll say, oh, where did this problem come in? Because I'm giving you old exams that cover almost to the end of the semester, and I've given you sample quizzes that do cover through the end of the semester. So there's material in there that you'll be using beyond exam 2. So I want to make that clear when you're looking for resources, wondering what to do, what can I do to study. There's good stuff in the sample exams, and I'm not going to be giving you any more sample exams for the final because I don't do that. You'll have sample stuff in the quizzes and in the exam too. So final exam 8 to 10 on May 12th, and then project 2 will be due on Wednesday. We'll be looking at that today. It's got 90 points, I think. It's got 4 tasks, and it's all digital communications. Any questions on this guy? Has anybody noticed anything that doesn't make sense? Because remember I said I will repost this. This is the roadmap I created last weekend. The weekend before last, saying how am I going to navigate this and how am I going to guide you to get through it. So use this as a point to go back to and look at as needed. So what's coming down the pipe? There's no new postings or repostings of homework assignments. There will be this that we'll talk about later. This is now filled in. I've got sample quizzes and 2 sample exams for next week that you'll be looking at. And then I've got to create a new exam for next week, probably starting tonight. And over here in the Python projects area, I said coming soon. You're going to see a preview of it. It's in much better shape than the last project because this is basically a rework of an older project. So we'll get into that soon. So I guess I should take a look. We're in phase lock loops right now. The homework problems that you're working on right now. Let's just get that page up here if it's not already. Don't need that one. So I'll be talking some about this. In particular, I'm going to talk about problem 21. That's probably the hardest problem, and it's the bonus problem. But it's out there as a challenge, and I've got, kind of like I did last week, I've got my solutions up on my tablet that I'll talk about later. Meanwhile, back over in phase-locked loops, we've got, we're going to pick up and jump down to where we left off, but just as a quick review, this is the basic model of a phase-locked loop. Actually, it becomes more generic than that because it actually has a loop filter. Well, never mind, the loop filter's in here, it's in a different order. But this is what we were talking about last time, and there's quite a bit more to go through on phase-locked loops. For those of you that took control systems already, there's going to be a lot of little overlaps in here, and you'll see how it blends together. And if you've just had signals and systems 2 only and not taken controls yet, you've seen some feedback and block diagram work, and I'm going to be looking at block diagrams immediately when we get going on this. So what we did last time is we looked at setting up the basic first-order phase-locked loop with the sign nonlinearity, which is due to the phase detector. In other words, here we have a waveform coming in, and we have a waveform coming out of the NCO at some center frequency that we're going to lock to with our phase-locked loop. When we go and created this block diagram, we left a lot of everything intact, but now we went inside the argument of the input sinusoid and pulled out phi, and then we went inside the argument of the VCO output and pulled out theta. So now we're looking at the block diagram in terms of the phases of the input and the VCO output. It's the same block diagram, but we've just gone inside. And in a real phase-locked loop, you can't do this. I mean, you can go inside in DSP, but you can't really put your hands inside the incoming waveform and just look at an argument like we're doing right here. We have to be content with understanding that we have the input has the phi inside of it, and the VCO output has the theta inside of it, and work from there. But we were modeling inside of that. So after we got done doing this, we established the phase plane plot, which looks at the derivative of the phase error versus the phase error itself. And for the first order loop, we have this first order nonlinear differential equation, and that's what this is right over here. I don't know if you look at it the way I do, but I say that's a differential equation. Why would you disagree with me, or why do you think it is a differential equation? It's got variables in it, and it's got either derivatives or integrals of variables in it. So, and it's got a driving function, and then it's got one of the state variables in the system itself. The theta is interior to it, and the phi is coming in at the input, but then it gets converted through this modeling of phi minus psi is the same as theta, so we can use psi rather than phi if we want to as the phase difference. So this was cool. We started to play with this. We'll look at a little bit more in Jupyter in Python. But after we established that it does lock, as long as we can keep the amount of deviation we push at the input, in other words, delta omega on the input, which is the derivative of phi, is related to the derivative of phi, as long as we don't push it in such a fashion that this phase plane curve here, this sinusoid, can still cross through zero, then we can lock. And that's the big if part of it. And that's what this equation down here is saying, that as long as the input frequency is such that we're less than or equal to the quiescent frequency, the VCO, plus the loop gain KT on the positive side, or on the negative side, we get a total lock range of 2 times KT. And in this next homework assignment, you're actually working with this equation right here to establish what are the static phase errors when there's a delta of omega present in the first order loop. And those of you in the lab will see this firsthand because you're going to, in Lab 5, and I guess, when does Lab 5 start, do you think? Are you going to start it today, some of you, or not till next week? Okay. It goes through all of this stuff, and it's not a real long lab, but it's very nice because you get to do almost everything exact, because the function generators produce angle modulation, FM in particular, and you're gonna set aside the radio board that you've been using now, and then you're gonna go work just on the breadboard again, and or with the generators and the RF board. So this will come up and in solving a problem. So this particular equation will be useful in the homework for this week. An observation that was made right at the end of this discussion: when KT is large and the phase deviations are relatively small, in other words, the phase error is small, then the sign of the phase error is approximately the phase error. So up here in the block diagram, whether it be right here in this so-called baseband model where we have phi and theta, or in the original loop model, this phase detector becomes a linear operation in the phase plane, in the phase sense. So what the next step in the modeling is to understand what the linear model does. So this is the linear model now, where we assume that sine of the phase error is approximately the phase error, and now we can switch entirely to the S domain because we have a linearized block diagram for the phase locked loop. So understand that this only is an approximation, but that's part of the legacy that was formed by Signals and Systems 1 and Signals and Systems 2, was pointing you at linear time invariant systems, right? The fact that they're convenient to model things and they occur frequently in practice, or we approximate them. I mean, I can even take it to electronics and say, what did you do when you learned about a device and using it as an amplifier? You tried to linearize it so you could have a linear model, input and output. So at any rate, this block diagram takes everything to the S domain by just taking the Laplace equivalence. So the loop filter had an impulse response f of t. It's now got a system function f of s. The VCO was an integration, and in the S domain, an integration is a 1 over s. So these things are replaced. So let's go after the closed loop expression, and the closed loop expression we're going to go for first, and then we can get anything else from it, is going to be finding theta of s in terms of phi of s, and then the other variables that are in the loop. So your backgrounds are going to vary because some of you had control systems, some haven't, but you did do something with block diagrams in 3205, correct? Do you remember that? We had a block diagram and you solve for things. So I look at it differently, but the bottom line is you say, I'm going to write theta of s. I want to find theta of s from the block diagram, and I want to find it in terms of all the other variables. So the way I set up the math here is I just said I'm going to write out theta of s right there, and I'm going to say what is theta of s. So I want to know what it is in terms of everything else, and I just look at my loop and I just collect everything onto the right hand side. So I see that I've got phi of s is flowing around through kt, which encompasses all of these variables in here, plus kv, and it's coming around and picking up the f of s, and then it's picking up the 1 over s. So I know that's one component. So I have the theta of s is coming on through, or phi of s, is coming on through. But then I also have I guess a better way of thinking of this is I've got these things in here. So really, maybe the best way of thinking of it, 'cause I'm just trying to get my head thinking about this again. I know psi of S is first attempt at using my rubber tip pencil. It's not working too well right now. It's not working at all. I turned on a straight line feature and I'm going to turn it back off again. So that phi of S minus theta of S is sitting right in here. So I'm going to take that composite of what's sitting right here and drive it all the way around the loop and say it's equal to the theta of S that I see over here. So I have KT over S, and I also have, phi of S minus theta of S, and then I have the f of s. Because of linearity, I can rearrange things and put things in any order I want to. So that's theta of s. And then I go after writing everything in terms of theta of s on the left-hand side and phi of s on the right-hand side. So this, to get down to here, is just algebra, rewriting it. And once you do that, then you can go after the closed loop transfer function, which is going to be the output over the input. So theta of s divided by phi of s is the next step, and that's called the closed loop transfer function or system function h of s. And then everything else that sits on the right-hand side is the closed loop or the properties inside the loop, and that works out in whatever form you happen to like seeing it in. I guess my mouse is now doing something weird. My mouse isn't scrolling the page. So KT times Fs over S plus KT Fs is what the closed loop system function is. And from control system, some of you probably said, oh, I knew that right away. How about those of you that, I know two of you had it, this was kind of obvious, right? You just read around the loop and you have the parameters that are inside the loop that are going to come into play. And remember that KT is all of this stuff here. KT involves that and that. That's the loop gain all the way around, and it also includes mu, if there is any gain over here. So those all combine together to be KT. And then you have the f of s from the loop filter, and then the s from the integrator in the feedback path. It shows up down below here. So that's our first order, or that's our general system function. And for our application, we're doing a first order loop, so f of s is equal to 1. We are going to move on to higher order loops in a bit, but so that's kind of a done deal at that point. And I do believe I have to restart this app. I mean, I've had this happen before. It is acting not too cool. I'm going to try to get by without restarting it. So after we put in Fs equals 1, we get h of s as a simple first order system. So now you can see why it's called a first order loop, because this has got one pole in it. It's KT over KT plus S. So this is a low pass filter response. we can go ahead and come back to our model of what happens if we put a frequency step in at the input. So if we're putting an input in, which is a unit step function over at the input side, and then we're going to integrate that to get it in terms of, well, we have to integrate it to get it in terms of phi of t if we're thinking of this as being FM. So we integrate our input modulation. If it's FM modulation, it's inside the integral here. And then we look at what that does in the S domain, and we have a 1 over S squared. Why? Just thinking back to signals and systems. A step function becomes a 1 over S, right, in the Laplace domain. But then when we integrate a step, we get a ramp. And that gives us the 1 over S squared. Is everybody good with that? I know you've seen this before, but it's early in the morning and you weren't expecting it probably. I have to think about signals and systems from the foundation. So there's an S squared in there. So in my mind, when I see an S squared, I'm thinking a phase ramp or a frequency step. That's how I'm going to be thinking. That's how I want you to think about it. So if we're going to do our linear systems modeling now, our input is got the S squared in it, and we drive that through our system function, and now we're taking advantage of linear systems theory. We have h of s given here, multiply it by phi of s, because we're going to want to solve for theta of s, so we just bring this over to here. Phi of s in the S domain, A, Kf is the interior modulation factor of the FM signal source. A is the amplitude of our frequency step, because it's right there, and we pull that in. We have the we have the S squared. So now if we want to get theta of S solved out, we could do what immediately if we wanted to? What would you have done in signals and systems too? Is you would have done a partial fraction. You do partial fraction expansion, right, to find out exactly what theta of S is. But instead of doing that right now, we're going to move interior to the loop. We're going to back up, and instead of going after theta of S, we're going to go after EV, the control voltage, which is just, up here. So basically, we're just going to traipse on back over to here. And how do you do that in a block diagram? Or how do I like to do it in a block diagram? If I know what theta of S is in terms of phi of S, all I have to do is go back up in the loop to the other side of the VCO. And how do I do that? I just take this quantity, and to make it look like this quantity, EV, I just have to multiply by S and divide by KV. Does that make sense? If you don't like it, say so I make sure. I want you to feel fluid and comfortable. I'm not pulling anything mysterious out of here, because that's the cool thing about a block diagram system. You can just move around freely. If you wanted to move around on the other side of this, you would divide by mu. If you wanted to move with f of s through it, you could back up. You could go around that loop and probe at any point you want to with your math. I'm thinking I'm going to have to restart this thing because it's very awkward right now. There's a green line on there that's not moving, and that's a sign that it's crashed. At any rate, I decided to just go after EV of S, so I multiplied by S divided by KV, and then now we've got EV of S, and this is the control voltage to the VCO. And what do we think when we think of a phase lock loop? You think of the control voltage as commanding the VCO to move to a higher or lower frequency if you're going to put in a frequency step, because that's the whole idea. The phase lock loop is going to try to follow the input, and in order to follow the input, we should be able to study the control voltage into the VCO and say it should be following the frequency deviation of the input. So now we partial fraction expand this term right here, and then we can use our Laplace transform theory, lookup table idea with partial fraction expansion. The 1 over s is a u of t, and the 1 over s plus kt inverse transforms back to e to the minus kt times t. And I'm going to bite the bullet here and just say I want to restart this. Hey, it works again. I should have done it right away. I forgot how easy it was. No, it's not good enough to be my default. Frustrated with it. At any rate, now that we've got this back, we've done the partial fraction expansion, and then maybe the pen will even work now. That'd be asking for too much, probably. That's not going to work. At any rate, we can now evaluate in the time domain, and then we can plot the response. We can see as t moves along, the control voltage into the VCO is going to put out a time domain value that's a RC time constant type response, which you should have been expecting. If it's a low pass closed loop transfer function, it's going to have this classical RC step response. So we're putting in a step and we're seeing it rise up, and it's following the input. So the thing that I think the book wants you to understand is that, hey, if I want to demodulate FM, this point, the control voltage, is representing in an approximate way what's coming out of what the FM deviation is. And that was the whole starting point for this discussion last week. Can we use a phase lock loop to demodulate FM? Remember, we were looking at discriminators, ways of getting the frequency deviation back from the input FM or angle modulation, but focusing mostly on FM. So this is not like an instantaneous step, but it does respond as if we're sending it through a low-pass filter. So if you wanted to make it more general, where rather than being a frequency step, it was just a general modulation in terms of the S domain, we could put MS in here as the Laplace transform of the message, and that's that guy right there. And then we'd have a way of just saying, this is the type of response we're going to get. We're going to get this first order response from the closed loop. We're going to get a gain scale involving the VCO gain and the deviation of the received signals modulator, and then we're going to have the M of S in there. So that M of S could be Laplace transform of a phase relating to a phase step alone, which would be a delta in the case of this model here. It could be a sinusoid, so we can do anything we want to with it, and we can treat it as a linear system. Then the next thing is to say, if the bandwidth of M of t is W, much less than kt over 2 pi, and you'll be dealing with this in some homework problems and probably in an exam problem, kt, I'm going to take you back up this page here, because kt is in radians per second, because if we go way, way back, here's the definition of kt. So you're going to see that in a block diagram, or it's going to be given to you, whatever the case may be, but it's radians per second. But a really important thing about the first order phase lock loop that we've already seen is that the lock range in radians per second is 2 times kt, but if I take 2 × divide by 2 pi, I get KT so the Lagrange in Hertz is KT over pi. So we can work with that, with the dimensions there. And I'm just trying to emphasize the fact that KT is in radians per second. So don't get them confused. If you want to find the Lagrange out in Hertz, you divide by 2 pi, or down here, as I was about ready to do, what is the bandwidth of the phase lock looper? It's a first order response. So what is the cutoff frequency of our first order loop? If we're looking at the VCO control voltage, it's KT over 2 pi. And then W there has got units of Hertz. Sound good? Some more comments here. First order loops have a limited Lagrange. It's plus and minus KT radians per second, or KT over 2 pi Hertz. It always has a non-zero steady state phase error when the input frequency is offset from the VCO quiescent frequency, and that we saw last week with the phase plane plot. That was evidenced here, because when we put in that frequency step of delta of omega, it now locked, but it's now shifted above the phi of t equals 0 line, and then that produces that static phase error, which is through the inverse sine function. That's just a property, like I said, of the first order loop. We're going to go on to the second order loop here momentarily, but the other thing is that if we make the bandwidth large, then you'll say the step response is very fast, the bandwidth is wide, and how do we do that? We can just make KT larger and larger by increasing the gain somewhere, and you'll do this in the lab experiment 5, and then you get a wider bandwidth. But there's something nasty that goes on in a phase lock loop circuit, whether it be a digital one or an analog one in particular, and that is this spurious time constants aspect. What are spurious time constants in a control system? If you had control systems, I don't know, did Dr. Platt call them spurious time constants? Okay. Well, I'm a circuits designer from way back when. When I first got out of school, I was an electronic circuit designer doing PCBs and stuff. So a spurious time constant is just saying that, hey, this loop, even in the linearized model, looks pretty good, but there will be some processing that goes on in the mixer that's going to model this. If we go back up here to our original picture, in order to make, gotta go back up to here, in order to make this phase detector, which is going to be a double balanced mixer or some other electronic circuit, produce an output at baseband, we need to have a filter in the phase detector itself just to remove the double frequency terms. And those of you in the lab have experienced this already, right? There's always that double frequency term. So in a phase lock loop, no difference. There's something at 2 times the frequency. So we get rid of that with some filter. It might be just a simple RC low-pass filter, like made with a 50 ohm terminator and a capacitor. That is a spurious time constant. And then the VCO, if it's an RF device, it has an input here, which is decoupling the control voltage from the RF circuitry inside the VCO. So that forms another spurious time constant. And then loop filter might be made with an op-amp, or the loop amplifier, and parts of the loop filter will have some spurious time constants because op-amps don't have infinite bandwidth. They have something called dominant pole compensation. Is that something you still learn in electronics? Never heard that term? So you understand, though, that an op-amp doesn't have infinite bandwidth. It has a slew rate and everything. So it has the effect of a spurious time constant as well. Those spurious time constants, what they do in our linear model is it's like putting another set of terms in here. Rather than having just f of s, we're going to have an f of s. If you want to lump all those time constants right into here, there's another block in here that has some poles that are set at much higher frequencies than, say, what's going on with the loop filter. But as the bandwidth gets higher and higher, those spurious time constants start creeping in. And how they creep in a feedback control system is they cause phase shift, and they cause instability in the loop. So the loop will not maintain its single integrator, but introduces 90 degrees of phase shift. Instead, we'll have additional phase shift beyond what this 1 over s is doing, and those will start creeping in and making the loop become unstable. It'll break out of lock, it'll oscillate, and it'll do bad things. So that's what this bullet is about down here. I can't spend enough time in this class to go into that, but just increasing the gain of a first order phase lock loop just to get lower errors and wider lock ranges is generally not done, because you just can't get away with it without having the spurious time constants all of a sudden factor into your design. And I was sort of hoping maybe you had seen that in electronics with the finite bandwidth of an op-amp, because it's compensated. Did you talk about compensation that's built into op-amps? They actually put something called a dominant pole compensation into it to help make it roll off, so that you can wrap feedback around the op-amp with some network and not have to worry about the individual devices and their finite bandwidth causing the phase shift that makes things break into oscillation. Maybe another way of thinking about that is, did you ever have an op-amp start oscillating? And it's like, why is this thing oscillating? That happen to anybody ever? It generally will happen in an op-amp circuit if you're trying to get a lot of gain, and you have a wideband op-amp, and you have your op-amp on a proto board that has the capacitance, distributed capacitance. It'll cause enough phase shift that it'll make the closed loop become unstable. Because feedback that goes from negative to positive due to phase shift is where the oscillation comes from. That you surely talked about, right? Feedback is negative, that drives it down, but if it all of a sudden becomes positive because you get 180 degrees of additional phase shift, now your feedback is positive, and that makes things drive up, and it will tend to oscillate then. Okay, we'll look at a simulation of the first order loop, and then we'll move on and look at the higher order loops. So simulation is a good way to learn about phase lock loops, and I started off doing it in MATLAB, and then I used MATLAB Simulink. In this class, I also, in the COM lab, I used another block diagram tool called VisSimCom. I've used Advanced Design System from Keysight, which we used to use in the lab. But I'm now content to just use Python, or if I had my druthers, I'd use Julia just because it's faster. But they all can offer the same capability. A full circuit level simulation of a phase lock loop is challenging because you need to simulate every cycle of the VCO. And in DSP-based VCOs, we have that same problem. But if you go into, say, LT-Spice and build up a phase lock loop with a double balanced mixer model and everything, things don't always work really well because Spice has a way of messing around with the sampling rate. It sort of adapts the sampling rate per element, and it doesn't necessarily prevent you from having stability problems. But Spice does have a way of tying down the ceiling on the sampling rate or the sampling period. Does anybody ever run into that with LT-Spice? You built up a circuit and it doesn't do anything like what you think it should do. Does that happen? Okay, it has, I'll call it a funkiness to it, that it will just optimize. It will think it knows better, and it's going to try to do this, but then you can go in and set some of the interior parameters to make it work better with feedback networks. And Dr. Platt, since he taught control systems and he loves Simulink manages pretty well to keep things stable from just the model itself. The way I do it in the Python simulation is we're just going to increase the sampling rate to make sure that there's no artifacts of significance from the simulation environment itself. We'd like to be able to do real bandpass signals, but we have to minimize the simulation time, and in particular, difficulties removing the double frequency term from the phase detector, realizing that in most RF scenarios, you're working at gigahertz, and your control system with the phase detector has got the baseband signal here, and the double frequency is just way, way, way out there. You're going to suppress it with a filter, but in a DSP-based simulation, you'll have to sample at a really high rate, and then modeling the feedback loop will just be very, very slow. So what we can also do in the simulation model is we can use the full nonlinear loop model, which is very good. And we can go with a complex baseband simulation, and then you don't have to worry about removing the double frequency term. All of these things are built into phase-locked loop models that are now in the module synchronization.py, which is part of Scikit DSP-Com, which that made me just think that we did upgrade it last week. It was updated because of the problems I was having with the coding, which I removed from Project 1, and I'm not putting back in. But has anybody upgraded their Scikit? I'm just thinking of a flashback, like I'd like you to have it up to date, because if you get to the point that you want to try something, this solves a couple of problems that crept in last week. So I got ready to do that last night when I was reviewing for today. So I was going to show you an example on how I would do it. Scikit DSP-Com has been 2.1.1. As of last Friday, it's whenever the day it was. It's not Friday because I was up in Denver. It's Thursday, I guess. It got updated, and it's now 2.1.2. So if I wanted to do that here, if I can type right. So the package name is Scikit DSP-Com, and I'm going to tell Conda, rather than install, I just want to upgrade, and let's just see if this will do it. Okay, let's see, how did I install my Scikit? Okay, so Conda is not working for me because when I originally set up my environment, there was a problem with Scikit not being on Conda. It's now on Conda, but I installed it with pip, and pip is synonymous with the PyPy, the Python package index. That's what PyPy stands for, by the way. So I have to, it doesn't recognize it with Conda, so I have to go down to here, and instead I have to do pip. And then here's what you want to do to remember it, since I don't remember it all the time either. Pip is the syntax is different, so I'll just cheat and I'll say, how do I do this? So when you're doing it with the package installer for Python, which is part of the native Python, you would say install, and you would say install the package. I'm not installing pip, but I'm just saying I'm going to install Scikit DSP-Com. But then it will say, you already have Scikit DSP-Com. What are you talking about? You don't want to install it again, do you? I'm wanting to tell it, I'm like grabbing it, saying, wait a minute, I want the newest version. Oh, okay. So you have to put in -- upgrade, and then it should work. So let's go that way. It happened really fast, right? It's done. And notice what it says at the bottom: successfully uninstalled 2.1.1 and successfully installed 2.1.2. So it's there. I recommend it, but I'm not going to insist that you do it. It's just pretty easy to do. And if I wanted to get rid of it from pip install, I could have removed it, and then I could have gone to Conda and installed it as a Conda managed package. But okay. Sorry for that diversion, but that hit me saying I needed to do that. So at any rate, we're going to do this model, and we're going to simulate everything in the discrete time domain. So we're going to use sequences rather than actual waveforms, and we're going to have a particular sampling rate, fs, which is 1 over the sampling period. And this is a model that was originally Dr. Zemer had in the book. And when it comes to needing an integrator in the loop filter, he does a trapezoidal rule model. So this is what that model looks like for trapezoidal integration. You might vaguely remember that from calculus or somewhere. Trapezoidal rule, does that jog your brain in any way, shape, or form? I mean, the trapezoid has to do with finding the area under the curve as if it's a trapezoid, right? The waveform is moving, and you're wanting to find the area of the trapezoid, so that's what this formula is right here. That's embedded in this PLL1, and PLL1 is in the synchronization module. So this is a generic function in the sense that it can handle multiple loop types, first order loop. It can handle a loop filter integrated with lead compensation, which we'll be talking about, and it can handle just a plain low-pass filter with for the loop with lead compensation. And these are what the f of s's look like. For first order, we just have a gain k. For the second order, we haven't talked about yet with the integrator with lead compensation. This is what f of s looks like, and so on. You get to put in the VCO gain if you want to, or it defaults, and then you can put in the damping factor for the 2 second order loops and turn the phase detector from being a pure linear idealization to a true sinusoidal shaped phase detector. And then it outputs quantities like the theta hat is the terminology used here to represent the theta of the input rather than phi. It's just a notational change. You can output the control voltage, and then you can output the phase error. Here it's called phi. Up above in the notes it was called psi. I'm not doing this to make life hard for you. I'm just following the way it was written in the book originally. So here's the gory details of the function. We're going to just take it into a simulation example. So I'm going to switch over to Jupyter right now, and I'm running it right here. And what's going to happen is that I added the updates to the Python package, but unless I restart Jupyter, I'm not going to get them. So I don't need them right now for this example. So although I updated my backend in Python under Conda with a new Scicca-DSP-Com, in order to start using it, I would have to close this session down and restart it. So I'm not going to do that at this point. I might do it over the break. So here's the same PLL1, which is contained in synchronization.py, pulled out again. How do I know it's there? I could go over here to my read the docs page, And I could go down into the synchronization module, and then I could click on PLL1, and so there I'm in PLL1, and then if I clicked on source, there it is right there. I'm using this myself all the time because I have to remember what I wrote, and when I was trying to figure out why things were crashing last week, I was checking what's in the repository. So by the way, the read the docs, I'm pretty sure was updated because it updates automatically the way Tronth has this figured out, or has it worked out. This was already updated to reflect the latest build, which was rebuilt and then pushed up to GitHub last week. Okay, so back over to this. I don't think I've restarted this notebook, so I'm just going to go down here into first order phase lock loop simulation. So this right up here is not what I'm running in. I'm using the PLL module. I guess I ought to show you how I did that, what the alias is from the beginning here. I'm aliasing the dot synchronization as PLL, which is more logical for our purposes, but there's digital comm synchronization algorithms in there, so you can give it whatever alias makes the most sense for your needs. So here I'm setting the sampling rate at 1000 hertz, and I want to look at first order phase lock loop that has a gain in hertz, KT over 2 pi of 10 hertz, which means the lock range is going to be plus or minus 10 hertz like we've been talking about, and I'm going to put in an input that does this sort of behavior. It's going to start with an 8 hertz step that turns on at a half a second into the simulation, and it's going to bounce back with a minus 12 hertz step that turns on at 1.5 seconds. And now you might be saying, what is this t minus 1/2? What is that all about? Well, I'm putting this in as phase, so that's a requirement of the way the phase lock loop works. The phi is the input phase, so I'm having to put in a phase ramp. Does that make sense? We're talking about how a frequency step is a ramp in phase. So I'm just ramping it. And the t minus 1/2 is so that it corresponds to the unit step at 1/2. So I create that phi down here. This expression right here is exactly tracking with what's up here. And then here I'm going to drive my PLL1 with that phi value, putting in the next argument, or I can just do Shift Tab and I can see sampling rate. Loop type is type 1, which is first order loop. And then I'm going to let KV, the VCO gain, just be 1. And it actually, KV in the model would be KV in radians per second, but in this simulation model, it's in hertz. So it's the sensitivity of the VCO in hertz, which is what you'll also do in Lab 5. You'll be working with the VCO that's part of the function generator. And I'm setting the loop bandwidth, or in the case of the first order loop, it's called FN, to be 10 hertz. And then the damping is set to 0.707, but that doesn't get used for this loop. And then the last attribute just tells me whether nonlinearity is turned on or turned off. So when it's 1, it's turned on, and it's off when it's 0. It doesn't take default values because I didn't write that when I wrote this code. So it just ran, and I set my simulation up to run for 2.5 seconds. So that's why it ran really fast. And now I'm going to do a plot here. So this is the VCO control voltage that's coming out. It's saying it's in quiescent condition, and it comes on to the simulation locked up, and then at a half second it's going to jump up with the RC low pass type response of the first order loop to 8 hertz, And then at 1.5 seconds, it's going to pull down a total of 12 hertz. You know, it's up by 8 already, and it's going to go down an additional 4. So that's a net value from here down to here of 12. And then it just rides along at that point. If I wanted to plot the phase error, I called it psi here, and I collected it out here as psi to more match the notes when we were for the first order loop. So then I can plot that. And this is the phase error that gets generated by the loop to match the 8 hertz step, and then to match the minus 12 hertz step that comes along. So these values here and here, where do they come from? They come from the expression we were looking at over here in the notes. They come from this purple, the purple boxed equation. You would put into that what KT is in radians per second. It's 10 hertz times 2 pi, and then you would put in delta of omega of 8 hertz, and then take the inverse sine of it. Sound good? And if I put it into a linear loop expression, then it doesn't have the inverse. You'd have to calculate it in the linear model sense, but here we can calculate it in terms of the actual nonlinearity of the loop. So the next thing that I did in this, I said, let's just try to look at the phase plane. We drew it out before, and let's just look at it exactly. So I went to the psi that I already had exported from the loop simulation, and I did a diff on it. So what is diff? It's part of NumPy. So diff takes the difference between inputs along array values along the array itself. So the first difference is given by, and I call this the backwards difference, but it's going to take the next value minus the first value along a given axis. If you don't put in any value, diff just takes the difference along the principal axis, which for a 1D array is just the array, the only active dimension. An important thing to understand when you do diff, though, is that the output is going to be one value less than the input array, because in diffing, you end up using pairs of values. So as you step down the array, you end up with one value less. So what I have to do to compensate for that, I'm going to plot the psi value on the x-axis, but I'm going to stop one value from the end. So in Python's colon notation, the -1 means I'm going to go from the beginning, because there's nothing in front of the colon. I'm going to go to one value back from the end, and that's what the -1 means. MATLAB would be different notation. So if you haven't tried this yet in Python, you can get experience with that. As a matter of fact, why don't I just pretend that I'm ignorant and just put a colon in there, and then it's going to take the whole array, and should come down here to all my error message saying x and y must have same first dimension, and it's like slapping you over the head saying you're a bad person. You put in shapes of 2,500 elements and 2499. Does anybody feel like this whenever they get an error message in Python? It's like you're beating me up. What did MATLAB do that drove me crazy? It would ding at you, right? Does anybody remember that? So it's the same idea. And generally you start at the bottom because that's where the final statement is made. So -1, go up here, put that back in. And now it's good. It's very happy. So I added extra dots in here, the start point and the end point. So this is like the phase plane plot we were looking at earlier, except I didn't animate it. So now this is animated because it's over time. It's actually operating over time. So it started here, 1.5 seconds in. There's no time axis on here. It's just psi of t and d psi dt. But I know it starts here, and then it jumps up by 8 hertz, but in terms of radians per second, it's going to be whatever this value is. It's 8 times 2 pi, and then the loop time constant is making it head towards 0, where it's going to be happy. If it can cross through 0 for the frequency error, it'll lock up, it'll come back into equilibrium, and then at 1.5 seconds it jumps down minus 12, and then it eventually comes over to here and pulls into lock. What's confusing about the phase plane plot is it's not linear with time increasing. Instead, it's just looking at 2 variables. So the fact that you can go from here, go forward, and then go backwards is just the nature of how the variables are changing over time. And this little shape in here, the fact that it doesn't look smooth here and here, has to do with the numerical integration. It's not perfect. But in the notes, I went ahead and wrote on top of this, put some notes on top of the picture. I said the 8 hertz step is 2 pi times 8, and that's this value here. And the phase error, when it finally locks up, is 8 hertz over the bandwidth of 10 hertz, inverse sine of that. There would nominally be a 2 pi in the numerator and denominator here, but they cancel, so that's the phase error that we have when we're locked. And then when we push it back in the other direction, we jump down to minus 75.4 radians per second, and then it drives back over to here to now have a negative static phase error of minus 4 hertz. That's what's netting out. Plus 8 minus 12 nets out to minus 4 over 10. Does this make more sense? It's bizarre, I know. It's not something that you're used to looking at, but it just all adds up, and this is something you could go back to when you're working the homework problems even, and just say, what is really happening here? And I understand, because I've taught the phase lock loop course I developed, and I've not been a big fan of phase plane plots, but I'm just trying to follow suit with what's in the book and give you something else that you can kind of tune into. So the next thing I did in the simulation is I jumped it by 12 hertz. And if the lock range is plus and minus 10 hertz, a total of 20 hertz, but we're quiescently tuned to 0 hertz, 12 hertz is going to be 2 hertz over the lock range. So what's going to happen? What's the loop going to do? It's going to jump out of lock, and it's going to just beat itself to death to try to get into lock. It will unlock, and then it will cycle slip indefinitely. And in terms of the phase error, it looks like this. It's just climbing and climbing. It's trying to catch up. It's trying to pull in. But in the phase plane plot, it's not going to be able to cross through 0 on the vertical axis. So this is what the control voltage looks like. And I'll run the simulation for this, but the way I explain this is it started at 0, and then at 0.5 seconds in, it shot up trying to catch up, and it pushed all the way up as far as it can go with 10 hertz, but that wasn't enough to lock with the 12 hertz signal. So it just slips a cycle away, and then it tries again, and it's hopeless. It can't do it. It just cannot cross through 0 on the d phi or d psi dt axis, so it just keeps slipping cycles. In phase lock loop theory, or people I learned from when I was in industry, this would be called a beat node. It's because it's producing a frequency error. This is not a pure sinusoid, but it's something that is beating. It's like it's producing that 2 hertz error is what it's doing. It just can't get there. So when you see something like that in the phase lock loop, you say, I'm outside the lock range, and those of you taking the lab will experience this, and then you'll dial it in and it will lock up. If we go to the phase plane plot, it makes a little bit more sense here, thinking that it shoots up to this value, and then it tries to cross through 0, so it tries to come down here. It can't get to 0 because it doesn't have enough bandwidth in the loop or the lock range is not big enough. So it flies back up again. It just keeps trying, and it can never settle to 0 where it will be stable. Go back to the simulation for a moment here and just take a look at that. So here I just simply step up half a second in to 12 hertz. And we can look at the phase error plot, or we can look at the control voltage plot, and it's not making it. So kind of a cool thing to do is say, let's just make it really close. 10.2. That's still above the lock range, so what is it going to look like here and down here? It's beating, the beat note is much slower, it's only half a hertz. But it's hopeless. It's just walking away phase-wise because it cannot get there. So now let's just drop this down to 9.9. It gets there, and here the control voltage gets there. It's not settling in. Well, it is settling. It's got the first order response right now. So it's not supposed to go up to 10. It's going up to, according to my model, it's going up to 9.9, right? I'm putting a step size of 9.9. Is this kind of making sense? Those of you that have the luxury of being in the lab will get to see this happen on the scope, and et cetera, et cetera. So it's pretty cool. At least for me it is, because I decided to become a phase lock loop fanatic at one point in my life. I mean, in teaching the class and everything. When I went to industry with my master's degree, I had some phase lock loops, but my very first project in the laser communications program had a synchronization loop, a bit synchronizer at 500 megasample or 500 megahertz, and right then and there, I was like, I don't know enough about phase lock loops. I didn't really know what I was doing, and I was trying to make something work. My box was upstream from several other boxes downstream that had senior engineers working on them, and I'm a young engineer, and I'm very intimidated by this. My box has to function before theirs can even get good signals. So I basically had to buckle down, and at the same time, where I worked out in Arizona State was offering a class on phase lock loops that was taught by one of the doctorate engineers in my group at Motorola. So I decided to take that class, and then that inspired me to eventually want to have a phase lock loops class here, because that calmed my nerves down to have something to work on. I don't know, has anybody ever thought what it's like when you go take your first job and your assignment has got some component to it where you feel weak and you feel like, you're maybe gonna not look too good to your manager? I realize you haven't thought about that yet, but you'll probably be in a situation where you'll be reaching out. So definitely reach out. Don't just sit there and stare at the wall. And various jobs I've had, the boss man will come around, or boss woman, I guess. I've had both types, but they come around to your office and say, so how's it going today? Show me what you're working on. Show me what you're doing. And they're checking up on you. So those types of things do happen, and you want to be able to talk about stuff. And they might not know the answer because they're the manager types, but they will put you in touch with somebody in your group that can help you with that sort of thing. So we're going to jump over, but I think we'll take the break now. We'll come back and we'll start on second order type 2 phase lock loop and spend some time on it. And then when we come back from break, I also, and you may have to glare at me, go through the exam 2 stuff. And then I also want to go through an overview of project 2. for where it stands right now. It's very close to being pushed up there, and have no fear it's going to get out there because I have to get it done before I leave. I really don't have, I'm not liking it, but I have no choice, right? I have to cram everything in with everything else in my life before I leave this week. So, okay, come back at around 9:30 would be good. We're just back from the break time, and a question I had at the start of break was, where are these audio files that you need in Project 1? They were contained in the zip package for Chapter 3's sample Jupyter Notebook. And I figured everybody had gotten those weeks and weeks ago, so they're inside here. This is just browsing it. So let's take a look at the second order phase lock loop, and then we'll move over and do some other stuff. So the second order phase lock loop has different variations in it. There's a third order phase lock loop, and at the end of this section we'll talk about what are the reasons why we want to have higher order loops, especially in space communications where Doppler is present. So first order loop has the problem with the spurious time constants. The second order loop kind of mitigates that very nicely because it puts an extra integrator in the loop, so this causes the roll-off a pole at 0 in f of s, and that just makes sure the spurious time constants do not come and haunt you with unwanted phase shifts. So this is called the integrator with lead compensation, and that's a term that would come from control systems, right? Those of you who are in controls, integrator, lead compensator. So this is what the loop filter looks like. So it's an S plus A over S, and A is a time constant, and then there's a perfect integrator in the denominator. So this is also referred to as a perfect second order PLL, since now there are exactly two integrators in the loop. There's the VCO introduces an integrator, and then you put one purposefully in the loop filter. There's also a homework problem 428, which analyzes the lead lag loop filter. And these three loop filters, the first order, the integrator with lead compensation, and this lead lag filter are the three types of loop filters that are implemented in the PLL1 that we were looking at in simulation. It used to be that when you were doing an analog design, this would all be done in electronic circuits with op amps or other passive circuits with capacitor and resistors. Nowadays, these same loops are implemented in DSP as digital loop filters. Same ideas though, same basic philosophies are involved. So if we jump right in now and replace f of s, replace the loop filter with just f of s, we have this back again, which we were looking at in general, and then we can go ahead and expand that out, and for integrator with phase lead, and we get this is the second order loop filter. So now let's go ahead and take a look at what happens with this second order loop with the integrator and lead compensator type loop filter, which is the one right up here. So we can define a transfer function g of s as being now in terms of this is called the loop phase, or the phase error closed loop transfer function, which is just 1 minus the closed loop system function from input to output. So we have these two types of transfer functions. So I'm introducing a new one here, but it's just 1 minus h of s. It's also part of standard control system. So this is what it looks like in terms of the phi and the theta in the S domain. And this is what it looks like for the closed loop error function. And then we have the standard transfer function. In both cases, though, we have this standard second order denominator. This is what it looks like in terms of our loop gain K, T, and then the time constant A, that's the lead correction. But in second order systems theory, in particular 3205 and control systems, you have the opportunity to have an underdamped system which has a damping factor zeta, and it has a natural frequency omega n. So this is the standard notation, s squared plus 2 zeta omega ns plus omega n squared. And so these are, I shouldn't do that because it'll get too echoey. These are the two parameters and how they're related. So a lot of times when you design loops, or essentially all the time when you design loops that are second order, you want to know what the natural frequency is in radians per second. And then you want to know what the damping factor is. When noise is present, you have another parameter that comes out of this, which we're not really going into. You have Bn is the noise bandwidth, and that's through an equation that involves both omega n and zeta. We're not needing it here, but that can be also utilized in your modeling. Bn would be in hertz. It's the single-sided loop noise bandwidth. But these parameters are control system specific, and they apply here as well. So let's look at what happens when we put in a steady state. We put in a frequency step, and the steady state verify that the steady state phase error goes to 0. So we go back to what we were doing before the break, and we're going to utilize something from Laplace theory and control systems, signals and systems theory, the final value theorem. So we're going to look at psi sub SS, which is called the steady state phase error. And we get at that through this theorem, which says we take the limit as S goes to 0 of S times the quantity of interest. So we're going to go back up here to what we were doing with the first order loop. And remember when we were setting up the input to a frequency step, we had in our math model way over here. That was our input, right? Or we could write it in terms of delta F if we wanted to. A times KF was delta F in hertz, or in radians per second, I mean, and then we can write that in terms of hertz if we want to. So that's what's going on way down here. Delta of omega divided by S squared, and then that delta of omega can be divided by 2 pi to be the frequency step in hertz if we want it to be. This is our closed loop error function, which was obtained right up here. Plug those two together, multiply through by S, so we cancel out some of the terms that are in here. And what we do is, you can see if you take and bring the S in, this becomes, this S cancels, so this becomes just S, and then it goes away, and then this eventually becomes just S all by itself. So we have delta of omega times S over S squared plus KTS plus KTA. And if we let S go to 0, which is this is the final value theorem, we see that we're going to get 0. Because this denominator, these two terms go away, this term survives, but the numerator has the S in it, so it also goes away. It's 0, so we get 0. And that's a really, really, really nice thing about the second order loop with the perfect integrator, is that it has 0 phase error in steady state. So that makes it very desirable. And we have the ability to adjust the response time through the damping factor. So we could take the inverse Laplace transform by backing up through this math and not doing the steady state final value theorem, just taking the inverse Laplace transform of the loop error function, having a frequency step of delta of omega radians per second, and this will be the transient response of the second order loop when damping is less than 1. And generally the damping is set to 0.707. Those of you that took controls, what makes 0.707 so exciting or such a great interest? I'm just curious what the latest is on why 0.707. You guys have an answer? I'm just curious. What's that? What are you saying, Sam?
The square root of 2, when you get 1 over that, you get 0.707.
Yeah, I understand that, but why is 0.707 a damping factor of interest? It has to do with, you can speed up the transient response when you make damping smaller, right? And this you learned in circuits a long time ago. You can make it speed up, but then you introduce overshoot, right? When you speed it up by making the damping less than, critically damped is 1, less than 1 is underdamped. But it's a combination of making it rise faster, but trading that against the amount of overshoot. I think 0.707, it's usually around 20% overshoot or something. But then in noise theory, which we're not looking at here, but I mentioned the loop bandwidth, the 0.707 is actually an optimal value for a tracking loop in noise too. So it just becomes a very popular solution. So here's an example going back to the 10 hertz for Fn in the simulation model, but setting damping at 0.707. So KT to get that would be 88.84. A, we can solve for that as omega n over 2 zeta. Remember these expressions. You can merge these two equations together to get an expression for zeta where you eliminate KT and you just have omega n in there, and that's what's going on right in here. So A is 44.43, and if you're doing a circuit design for this, an analog circuit design, or if you're doing a DSP design, you would have to get the integrator constant would be A, but if it's a circuit design, you want to convert it to resistors and capacitors generally. In the Python simulation, you don't have to do that at all because it's already been built into the simulator engine. When you put in 0.707 over here and we change the loop type from 1 to 2, which is right here, this automatically calculates inside the calculations. So it'll run as expected. So here we're going to put in a large step of 40 hertz, set delta F equal to 10 hertz, which followed suit from the first order example, leave KV at 1 hertz per volt, and then it calculates other terms to make up for that inside as well. So do this calculation, and there's what the second order loop VCO control voltage does. It's actually slipping cycles because we know in the first order loop with only a 10 hertz KT, or 2 pi times 10, the loop did not track at all, but because we have this integrator, it's able to eventually integrate up and pull in with a 40 hertz error. So that's a really nice property. This would be called cycle slipping, and there's equations that can model how this works in theory. Obviously, if I make this 10, just rerun it again, you're seeing the overshoot, and then it's pulling itself in. If I was to make this, say, 8, like we did originally, we're still going to see overshoot, but we're not going to see quite as much because we're now fully linear. We're approximating more or less the linear response, whereas the nonlinear behavior, which we can control by this, if I go to the linear loop response, these two are going to look the same, whereas if I jack this up to 40 and leave the loop as being linear, it just tracks immediately. Now, that's because I took the nonlinearity out, and that's what makes phase-locked loops more challenging than linear feedback control, because we have this nonlinearity. So you're deceiving yourself if you leave leave this in linear mode, because this is not the linear behavior. I mean, this is not the way the loop will behave with a sinusoidal phase detector. So we end up seeing that we're slipping cycles, but we still do pull in due time when we make it nonlinear. Interesting. I mean, this class we can't drill into this very far, but I find this stuff very exciting myself. Because in comm systems where you have to synchronize the carrier frequency, and then you have to do a bit sync, or in the spread spectrum that I'm doing now, you have to do a spreading code lock. You have a tracking loop that's second order, and you have these behaviors to check out and tune up as you're getting your loops working to do your link. I also did the phase plane plot for this. So this is what it looks like when it's pushing it hard, like I said, at 40 hertz. It's slipping cycles through here, but it eventually get its act together and it can cross through zero. That's the critical thing. But it's not able to stop right here. This is a nonlinear second order differential equation. I'm not attempting to solve that. I'm doing it numerically here. But it eventually swirls around, loops around a little bit more, and then finally comes in. If I was to take this down to 8 hertz like I did moments ago, and then look at the phase plane plot with only the 8 hertz, it jumps up, it's out of lock at that point, but then it's trying to capture and drive the frequency error back to zero. So it circles around, it can't stop there, it doesn't have the ability to do that, but then it eventually locks up. And notice that it locks up with zero phase error, because that's a property of the integrator. It can get the phase error dialed out to zero, which the first order loop could not do. And I should take this back over to 40 again just to verify or let you see that it's definitely doing that. Well, actually, in this case, what is it doing in terms of the model? It's not bringing the phase error back to zero, but this is a 2 pi, a mod 2 pi thing. I put this in the notes, I'm pretty sure. So it slips 3 cycles and then it locks up. So it locks up 3 cycles later, which is 6 pi. Sound okay? I mean, you don't have to fully understand this, but in a modulo mod pi kind of a system, you can't lock within the first cycle, so it doesn't have truly zero phase error, but if it has a multiple of 2 pi, it still has zero phase error. If it was a digital comm link or something, this cycle slipping operation just would say that you're going to miss some bits. Some bits are not going to be recovered because you're slipping. Okay, what I also have in the notes, and this is this was a function I had many years ago in MATLAB called PLL1, and then it was turned into PLL2. So I didn't rewrite this code. I have it in the notebook though, because I have another loop in there, but I just set up an entire bandpass simulation to actually take in a bandpass signal with the phase lock loop. And this was done in MATLAB. I don't have this exact example in Python, but I could construct it. Instead, I have a complex baseband phase lock loop. But this just set up to say, let me model what it would be like if I was at some carrier frequency wanting to lock to it and approximating the removal of the double frequency term with a Butterworth filter, and then show that ultimately that when the loop locks up, the carrier frequency is 1000 hertz. In this simulation, put a frequency step in of 20 hertz. It goes through a transient period. The VCO control voltage recovers a message at 10 hertz and life goes on. I mean, you will also look at this in the lab with your first order loop, the fact that you can lock to a carrier frequency and then look at the control voltage on the VCO, and you'll see the FM modulation is recovered. The complex baseband phase lock loop is incorporated into the PLL, or the synchronization package, and it looks like this. This part of the notes was never finished. I mean, I didn't rewrite them. It's in the Jupyter notebook, though. This was what I was struggling with a few weeks back when I was getting further behind on Project One, because I was trying to tune this up. I will eventually fix this, but it's not on the top of my list right now. There's too many other things I want to do, but this starts to describe how the complex baseband phase lock loop works. And like I said, I'm pretty sure it's in the notebook here. It's just called PLL_CBB, and instead of putting in a signal that's a real sine or cosine, it's a complex sinusoid, and you can set its frequency to be any frequency you want within, less than half the sampling rate. And then you can put in a phi on top of it, and then the NCO puts out, or the VCO puts out, a complex sinusoid in your phase detector, rather than just being the sine of the arguments of the two input phases. It ends up being the imaginary part of the real signal coming in, and the VCO output signal is a complex sinusoid with a conjugate on it. So this is a little bit more sophisticated. I'm pushing well beyond, what the book wants you to look at, but it's in here, and I'm not going to really dwell on it too much. I'm pretty sure this works, though. This is a closed loop response to just see that you get the VCO control voltage recovers the modulation, and then this is the phase error, and this is a first order loop, I believe. I just didn't do a whole lot more with this because I'm going way off there's no homework problems that do anything like this. But all this stuff can be done in modeling and in simulation. So now what I want to do, I'm going to stop right here. So this sort of sets, I guess I should do I'm going to do one last thing. I'm trying to set my end point for exam 2 is what I'm thinking of right now, what we've covered up through to this point and what will show up on the exam. So the very last thing is this general loop transfer function in steady state error. So it goes back to the original closed loop transfer function, the closed loop error function, 1 minus h of s, and then this is in the book as well. It says what in receiver tracking applications, like for satellite communications, we will use a phase lock loop to lock onto a carrier or a clock of some sort, but we need to consider platform dynamics. So we're looking at phase deviations that are going to come in the received signal. And this is not something that you set out to do, but it's just because of orbital mechanics. Or if you're driving down the highway, the same thing would happen. If I'm standing here and you're driving away from me, you would have some profile as well, some platform dynamic that would exist. And this model just says that, okay, we're going to have 3 terms as an approximation to simplify things. Actually, what you do with your accelerator and how you drive will be more than acceleration and velocity and position, but these 3 components are generally the way things are classified. So we have acceleration, or this is a rate of frequency error or frequency deviation. This is a step of frequency, f delta, and then that's the phase. So in applications, like I said, this would be platform dynamics, where you would have acceleration, velocity, and position. I'm making you think now. I want you to think in terms of physics from way back when, where you had standard mechanics, right, where you had something moving and it had an acceleration and it had a position at any given time instant. So that's how it shows up on the Carrier phase. Let's say as a function of time, this would be the rate, this would be the step, and then that's the phase due to position. So if we take a generic model for this in the S domain, it ends up looking like this. A phase step is a 1 over S. A frequency step we've already seen is a 1 over S squared. And a frequency ramp is a 1 over S cubed. So now we can go to the final value theorem, and we can say if we bring in our G of S for a given loop type, along with this type of platform dynamic, and do the final value theorem, what we're talking about is seeing what makes G of S, what drives G of S in terms of what type of errors we're going to have in the loop error function in steady state. So here is loop filters. These are order types 1, 2, and 3. What happened? It freaked out on me again. Order types 1, 2, and 3. 1 being first order loop, 2 being the second order with perfect integrator, and 3 being a third order loop, which we haven't talked about, but is just thrown out there to say, okay, if a first order loop can track frequency but has phase errors due to static phase error, as it's referred to, a second order loop can track phase and frequency with 0 error, but with a frequency ramp it will have a static error. So we go up to a third order loop to get phase, frequency, and frequency ramps perfectly tracked. And that's something that people think about in space communications, but the downside of building the third order loop, which is what this piece corresponds to here in the loop filter, is that it's not conditionally stable. It's unconditionally stable. And what that means in a feedback control system is if the loop gain is such and such, there'll be a range of loop gains where it will be stable, but if the loop gain gets too big, it will go unstable. Or even in some scenarios, some types of loop filters, if the gain is too small, it will also be unstable. I definitely don't want to go into all those intimate details, but if this is the general G of S then for this type of loop model where A controls the second order loop component, B would control a third order loop component, then this is G of S. Yeah, stupid thing died on me again. I can't do anything. I'm going to kill it again and start it over again. Okay, now it's back again. So the idea here is with this model, and whether or not I want to give an exam question on this or not, I don't know, but this model now plugs in everything, plugs in the final value theorem, and then it says, suppose we have these components in our platform dynamic that introduce a phase error, a frequency step, and then a frequency ramp. And then if we evaluate the final value theorem, we can see what the possible steady state phase errors might be. We know for the second order loop, for example, we can handle the frequency step, but if we have the second order loop, in other words, where A is not 0, but B is 0, then we will get some steady state phase error out of this. So we could just carry this on through and let S go to 0. is what would happen. And we're going to see that if, for example, if that term were not present because we only had a second order loop, that's going to cancel this out. So that will be gone, and then what happens is S goes to 0. This term comes through, and this term comes through. So we're going to get so we have a steady state phase error with a frequency ramp component. And you could pick any other variations on that you wanted. Like suppose you put in the first order loop and A was equal to 0 in this case, then you would have, you're going to find out what's going to happen is that you're going to have a steady state phase error that goes to infinity because it can't track the frequency ramp at all. It just drives it off and goes out of lock. So I'm kind of rambling a bit, but I'm kind of getting at the fact that this was something that Dr. Zemer added to the book in the final edition that's out there right now that we're using, is just said, look at this equation. I put it in the blue box to say, what are some possible values? So you say, I only have a second order loop, or if I was to say I do have a third order loop, I could go back up here and I could say if I had a third order loop, then all of these terms are present and B in particular is not equal to 0. So this goes away, this goes back to 2. That's 1. That's gone. Now, because of the fact that I have the third order loop, this term right here, what's going to happen, did I do this right? I got to make sure I set this up right because now I'm getting myself confused. I will leave the S in there, I think is what I wanted to do. Yeah, that's what I wanted to do. I didn't want to take all those terms out of there. I'll leave these terms in here, and what's going to happen is S goes to 0. These terms all go to 0. But now this S comes all the way down here, and well, the S is up there, and it makes it go to 0, so that in that particular case, if I have the third order loop, my steady state phase error is 0 because that B is not equal to 0. So it's just how you work the algebra through. Okay, I'm going to stop. I'm not saying I'm going to give you one of these. We'll look at the old exams because I don't remember whether I had anything on here that used this equation, but it certainly is out there, and maybe it will show up on the final. So I think what I'm going to do first is I'm going to give a quick overview of what Project 2 is all about, and then we'll wrap into talking about Exam 2. But before I do that, I'm going to do something in Project 1. In Problem 2, we're doing PCM, and what you're doing in here, I'm having you in the tasks associated with this part of the project, you are getting down to the tasks. And Natalie was asking me about this over the break, so that's why I'm kind of going on to this. Even though I omitted part 3, actually it's not in here where you send me the zips, it's in problem 1 task. Sorry about that. Jump back up to the first problem. There's 2 places in here where I'm asking you to send me a zip of a WAV file. least I'm remembering that they're in here.
In between all the two task one as well.
Okay, then you're probably right.
Oh, there it is, save and deliver.
Yeah, save and deliver.
I have them.
Okay, just send them to me. Those two there finished their project, but they didn't give me the WAV files. So where's the other one? It's in task. Maybe I didn't write save and deliver. Or maybe it was in 3, which we omitted.
And we have to, when we receive the audio signals back in task one, I think maybe you either said it in the part above, or I just assumed that you want the file.
I know you should be listening to it, but I don't remember. It's not jumping off the page here. So I'll take an action item on clarifying that, because I remember thinking it through, but my mind is kind of scrambled because I've been doing too many different things. So I'll look at that, but definitely you see one of them says save and deliver. I'm going to edit this document because I already said not completed. That was a remnant. This obviously is completed. Yeah, there it is. Listen and deliver. I don't see another listen and deliver in here. But it is under task 5. So there's where they're at. So I also look at this rubrics page because it kind of summarizes. It's what I do for myself so I can grade stuff. Okay, so we got that covered. Okay, so now I'm going to go look at what I've got done on Project 2. Project 2 is all digital communications, advanced digital communications in the sense that it's more than just BPSK, it's quadrature amplitude modulation. So I was going to add a part 1 to this, or problem 1 and problem 2, but I'm just not going to take the time to do that because I'm just pushing too hard with my trip and everything. I may demo that at some point. I could demo it today if I wanted to, but at any rate, it's the same setup as Project 1. If you're a graduate student, you have to work alone. If you're an undergraduate student, you work together. There's a lot of learning new things in this project and terminologies, and I'll just start by going to the back end of this document, which is going to be tweaked a little bit here and there, but there's an appendix I put in here on, let's see, eye diagrams, scatter plots, and waterfall plots. So this just goes through what eye diagrams are all about on a very basic level, shows you what they look like when you generate them. Scatter plots are sometimes called constellation plots. Scatter plot just shows you when noise is present and you're demodulating to get your bits back again. You have a cloud of points. And then I go into more detail on waterfall curves because you're going to be working with those in 2 different parts, 2 different tasks of this project. The basic idea of the waterfall curve is that you have the theoretical value that rolls down looking like a waterfall, and then if you have an impairment in your system, the curve is going to get pushed to the right. And generally in requirements documents for hardware that's delivered, you generally have something that says you can be pushed out so many dB at some operating point. So it might be at, say, 10 to the minus 5. So you might draw a line through here, and then you drop down effectively. And you're seeing how many dB out on the EB over N naught axes your performance is. And you're going to look at 2 things in this project. One is timing error and phase jitter. And phase jitter will produce an impairment like this that flares out. Timing error produces more or less a shift that looks like this. So you'll be analyzing things and you'll be taking measurements through Monte Carlo simulation where you're going to be getting you'll be getting points, be getting measurement points along here, and then you have to do some interpolation on, say, the purple points and figure out, say, at 10 to the minus fifth, how many dB, fraction of a dB is it pushed out. And that's talked about more up in the problem itself, but I'll also require you, when you're getting waterfall curve plots, to get at least 100 error events. And an error event goes into the calculation of the error probability. You're dividing the number of error events divided by the total number of symbols simulated, and that gives you an estimate of the probability. This goes into probability theory, and a fundamental experimental technique is called repeated trials, where you repeat the experiment over and over again, and you see how many events occur that correspond to errored events, and you divide by the total, and you then estimate that probability as that ratio. So I'll step down into this, and if I don't get through all of this because I need to jump out, I will talk about this in a video, and I'm sure it's in an old video, but it's a slightly different version of the project. So let's go back up to the beginning. So this is a top-level view of a radio RF type digital comm system. We'd come in and generate at the transmitter some data bits, and those data bits would be on an in-phase and quadrature, real and imaginary parts for the modulation scheme chosen. And it turns out what these AK and BKs do is they form what's called a symbol as opposed to a bit. A bit is just one piece of data in a serial stream, but when you're modulating in a higher order digital modulation, you use the in-phase and quadrature to create a symbol where the location of the angle or the position of the real and imaginary parts defines a symbol value. Like 4QAM is the same as QPSK. BPSK is just nothing on the imaginary part, only on the in-phase part. Now, I have pictures of that down below here, but then when you pulse shape, which is pretty much universal in digital comms of today, used in cellular, used in DOCSIS, which I talk about. Has anybody ever heard of DOCSIS? Data over cable is what it stands for. It's a standard that Comcast would use. And the fiber optic networks do something similar. I don't know what the standards body is for that. I'm just familiar with DOCSIS. Then you go through a digital analog converter, and then you put it up on a carrier for the sine and cosine, and now we have a radio channel signal. And we might have multiple co- and adjacent channel signals. And then we'll model our channel as having white Gaussian noise, which is on the real and imaginary parts, perturbing it, come around to the receiver, have a bandpass filter. This is all RF stuff. And then we translate it back down with a synthesizer back to some baseband frequency. And we bring in two parts into the receiver. And this is sort of the flip side of what you're doing in problem one of project one. You were doing it with just one A to D and using analytic signals. This is the more traditional way of doing it with two streams that you down convert to baseband with a sine and cosine, low pass filter to get rid of the double frequencies, but then you come into the A to Ds, and now we have a complex signal here, and we're going to decode our waveform. Where we put the symbols on through the AK and BKs, we're going to detect them back off following a matched filter, which is just a filter that matches the pulse shape. And it just so happens that we'll be using a raised cosine or square root raised cosine over here. And then this filter ends up just being a time reversed version of that filter. But in order to make it causal, it's shifted to be causal. And then we make decisions. So it's the math part of it. These are the two most popular pulse shapes that are around. The rectangle pulse shape was the way space communication started. The root raised cosine or square root raised cosine is the most popular technique today. And you analyze this in one of the homework problems, right? Remember, I had you play with the RRC or SRC. I already graded that homework. I didn't grade much homework yet, but I did grade this problem, I know. So then here's how we take and form symbols from data bit streams. So we have two streams, AK and BK. How do I get that in a general practice? Well, you could think of a stream coming in as a serial bit stream, but then you would take the even bits and the odd bits and just simply demultiplex them into two streams, and those would drive the AK and BK lines. And if you're doing a high order modulation like quadrature amplitude, the values that the AKs and BKs take on follow this pattern: plus minus 1, plus minus 3, plus minus square root of m minus 1. And when you put that up as a complex baseband signal or as a real signal, it looks like a cosine has the AKs and the sine has the BKs. But then as you form that back into the real part of a complex envelope, fundamentally the thing that we're most interested in is this, getting this back at the receiver. But we have to, oops. So hard to write, remove carrier. So we have to remove that carrier at the receiver. And not only that, we have to track it with a tracking loop, a phase-locked loop. Right here, it's just getting removed here, but then we have to track any residual Doppler and things that would be present in systems where there's platform dynamics, but none of that's being modeled right now in this setup. So this is what a quadrature amplitude modulated signal looks like on the right. On the left is just simple binary phase shift keying, which just takes on values of minus and plus 1 corresponding to 0 and 1. But the QAM is going to modulate both the real and imaginary parts. And this is 64 QAM, so it has 64 locations in here. And log base 2 of 64 is 6, right? 2 to the 6 to the 64. So these dots mean that each symbol now, a symbol is composed of 6 bits. It's used in DOCSIS, Wi-Fi, it's used in 5G, 6G, it was used in 4G. It's highly popular. You will experiment at the end of this project with going all the way up to 256 QAM. So it's a very, very dense constellation, and you're going to send audio through that, and you're going to incorporate the framing that you do in Project 1. And I've rewritten that code, and it's in the sample notebook already. I've made it a little bit more user-friendly, but it'll be adding the sync pattern at the transmitter and then at the receiver after it gets decoded, after the bits are decided, or symbols are converted back to bits. Then you will look for the sync pattern, then you will apply that to removing the sync pattern and then getting the bit stream back serially and then taking it back to analog through the PCM decoder. And by the way, the PCM encode and decode had a bug in it too that I fixed last week, but we were not broaching that because it only had a problem if you took it up to 16 bits per sample or higher, which I was going to demo that back in chapter 3, and then it crashed on me, and I was like this, scratching my head saying, what happened? So what keeps happening to me, and you can think about this over your lifetime as a career, you write software, you use it in simulation modeling, and then Python keeps iterating the way NumPy works and so on. And so you coded something, and then they took something out. They deprecated some feature, and then pretty soon that feature was gone. And when the feature is gone and your code used some feature that they deprecated and then it's taken away, what happes? Your code breaks. And if you're a package developer for Python or you develop it for your work, you've got to figure out how to fix your code so it can run still. You're not worrying about it now because you're young and you're not thinking ahead, but these things do happen. And it's been happening to me ever since I released the package. We have to fix stuff that breaks when we're using a newer version of Python. At any rate, it's all fixed now. I'd like to think it'll never break in the future, but it will always break some point in the future somewhere. It just happens. So we have BPSK and QPSK. QPSK is 4, and then we go 16 QAM, and so on, 64, and you will get to try out 256. So here's the serial bit stream. The IQ is flipping back and forth to form the in-phase and quadrature symbol patterns. Here I put some links in here. It doesn't work in this mode, but these links will be active. See if it takes me to where I put it to. What modulation schemes are used in 5G? So if you want to understand where these things show up, there's one particular example. So how do we make decisions? And this is what the receiver does. It will match filter the waveform, but it still has to get an amplitude value back at an optimum sampling instant, and you will explore that in the project. And for, say, the 64 QAM, you can think of any point in the constellation. We have to make a decision, and it's going to have noise cloud here. So suppose this is the symbol of interest. It decodes back to 6 ones. Noise is going to most likely push it either to the right or to the left or up or down. It's going to be less likely to go to the diagonals. So what do we do with the encoding? We encode it with something called gray encoding. Oops. Gray encoding ensures that the nearest neighbor decision is only differing by 1 bit. So look at this, 6 ones, here we see 5 ones and 1 0. So if we do happen to make a mistake, we're only going to hit up with 1 bit error. And likewise for the other 4 most likely error quadrants. Is that cool or not? I mean, I realize right now I'm blowing a lot of stuff at you all at once, but somebody thought about this, and gray coding is used elsewhere in computer systems, but it's used in modulation theory in particular. But we still have a finite probability of falling out of that, and with the white Gaussian noise channel and creating the noise cloud. The first project talked about using white Gaussian noise and looking at the probability of an error for BPSK of being just the tail of a Gaussian PDF. In the case of QAM, we've got the pulse shape filter at the transmitter, putting it up on a carrier frequency, and then taking it back off again, and then you would have a matched filter, which would be another square root raised cosine filter, which does a wonderful thing, something that's talked about in COM2, but it allows 0 intersymbol interference. I did not talk about this, but if you look at the pulse shaping in here, you see these wiggles in here. Well, if I convolve this SRC with another SRC, I get something where the wiggles of adjacent pulses cross through 0 at the pulse of interest. So you can make a bit decision right up here, and if there's an adjacent one of these guys, it's going through 0 right at the decision point of that particular bit. So it's called Nyquist pulse shaping, and it's optimum for white Gaussian noise. So that's what makes it so common and popular in applications. So I've got the gray encoding and decoding built into the function library, and then I also have a bit error probability test set built in. So the way we do symbol error probability checking, we use, for the theoretical value, we use a function called, oh, never mind, this is the simulation. I use a function to get bit errors called BPSK BEP for bit error probability, which works for the symbols as well, because we tested in the in-phase and quadrature. But I'm getting ahead of myself slightly. If this was with noise present, how are we going to get error probability calculations done in simulation? The function takes care of looking at all 64 clusters, let's say, and if they go outside the boundaries of that little square, we'll get a symbol error, but then the Gray decoding takes it down to the bit errors, and then we form this ratio. Bit errors divided by total bits, and that gives us the probability of bit error in the serial scheme. For QAM, this is what the math looks like for it, and there's a function that you will play with to create some curves in this project as well that looks like this on the inside, and then the BPSK is a special case of this, which has its simpler expression. So that's called QAM BEP theory, and it uses this equation for m is equal to 2, which is BPSK, and it uses the longer one for QAM. So the receiver model is in here, and I'm going to stop right now. I'm just going to have to say I'm going to spend more time on this in the video, or look for it in the video, depending upon how my life goes the rest of the week. But you will be doing measurements, and fundamentally you're going to be doing a number of different types of measurements. You'll look at eye pattern with the QAM, and this is what it looks like on the real axes, and it looks similarly on the imaginary axes. The idea is that you want to have the eye open so that you can classify your signal in one of these clusters. And if you look at it horizontally, you're seeing over time we should have distinct lines, because 8 times 8 is 64, right? So there's 64 total clusters along here. And when noise is present, the clustering it's not as tight anymore. I think there's a picture of that in here. It's not where I thought it was. But at any rate, you will explore that. And then at the very end, you will explore doing it with audio. So I put these functions in here. If you want to use these in Project 1, that's fine. I added the insertion of the sync pattern, and now I added the ability to turn the random shift on or off, because here we don't want to use it. In Project 1, I wanted you to use it for the first part. And then I also modified, let's see, finding the sync index. That stays the same. You can turn off this plot by default, which you use in Project 1, and then returning the PCM stream. I think that is the same as it was too. It might report errors differently, but it gets utilized in here in a very practical way, because this receiver has delay in it due to the filtering, and you need to resolve it, and this does it automatically. So this sample experiment here is an example of what you will do when you're going to do the last part of the project. And if you don't, you get this, but I'm going to change this figure. It's going to be this, because you're going to be finding the sync pattern in the receiver, then you'll strip out the sync pattern, and then you'll be able to decode the sync pattern free waveform and get it back again and be able to listen to it. With 256 QAM, this example was 64. I think I have to stop though. Okay, a little over 10 minutes. Let's talk about the exam. So what I'm giving you right now for the exam, the format of the exam is identical as the first exam. So you should write out another crib sheet. You can have your same printed crib sheet as you did before, okay? You can have the first crib sheet. I don't care if you want to say I have my first one. I don't want to change it. Keep it. Add to it another two-sided sheet that relates to the new stuff, okay? I don't think you need it. I think you need the new one. You don't need the old one. But if you want to keep it integrated, that's fine by me. I want you to have as much comfort, right? Security blanket stuff. You definitely need the sheet that has the trig identities on it. I think that's probably something you're going to definitely want to be using on this exam because we're working with modulation theory. So you'll have one two-sided, that's your old one, a new two-sided, and then you'll have the 3-page sheet as before. To support all of that, I've got old quizzes. So before we went up through quiz 5, now we have quiz 6, double sideband and AM. You can look at Hilbert transform and single sideband, some sample problems. This ended up not being a quiz, but this was a homework problem, right? I just simply recycled it into the homework category. I actually left a detailed solution of it in here too, based on some hardware that was available. Then sampling and pulse modulation, that's also in chapter 3. So that comes along here. It looks like I did not have anything on mixing, but those are in the old exam, so we'll look at that in a second. Angle modulation will be on the exam here. This is an example. Angle modulation with a VCO and setting up deviation, Carson's rule. So what I'm going to do is I'm going to pick, just like I did on exam 1, I'm going to pick 2 of these sample problems, not ones that were homework problems, obviously, but 2 of these problems, and they'll show up on the exam. What they're going to be, I don't know. Sound okay? I mean, remember we agreed last week we wanted to make it be the same idea. This is a question about discriminators. Something weird printed out there. I don't know what that is. It looks like the axes got messed up. But at any rate, PLL and PLL synthesizers. This one is the first order loop. So this is fair game. Second one is on synthesizers. We haven't covered that. So this is pretty much where this stops as being useful for this exam. But what's down below here is definitely useful for the final exam. So just remember that you'll have this available. And then Appendix A is in here too. A couple Appendix A problems. Okay, so what else do we have? The next thing to pay attention to is the fact that in the old exams, which are up here, exam 1 from 2019 and exam 1 from 2020, both had chapter 3 problems. They had at least 2 pages of the problems were from chapter 3. Look at those again, because that's stuff, those are examples of how things roll. This exam 2 from 2019 and 2020, let's just take a look at it. Here's frequency translation and mixing. This was part of chapter 2, or chapter 3, I mean, for sure. So it's a good thing to take a look at because a problem like this is going to show up, almost guaranteed. There was no quiz problem on this, but here's an exam problem on it. Envelope detection, carrier reinsertion, and then right away jumping into FM for the rest of this exam. So you definitely need to look at the old exam 1s for more types of problems for this exam. Got it? I'm sorry you have to correlate all this stuff, but I'm not really sorry. I mean, this is life, right? I'm struggling to try to make all this stuff happen. So just cover the bases. You got multiple sources, so this is not frequency synthesizer is not on exam 2. It will be on the final. But this problem is, so if you see something like synthesizer or the things that we stopped just above, it's not on the exam. And I have to do the same thing. So that's this guy. Take a look at this one. This one starts with Hilbert transform, so obviously there was AM and other topics above it. Bandpass sampling shows up in here though. So that's fair game. IF, double conversion receiver, very similar to what was in the lab. You guys played with this kind of a hardware setup, but fair game. Bessel function stuff. Remember, your crib sheet has got that last page on it that has the Bessel function table. So you're not going to have, unless your calculator has Bessel functions loaded in it, you're going to want to use that table for something. There will be something on the exam where you need to use the Bessel function table. Okay? And this one is an example of that. So I gave a picture and I just said, you know, make some deductions, and this used the tables. Another FM modulator example, frequency doubler. This is similar to something that was actually in chapter 3, but it combines that from chapter 3 and FM modulation from chapter 4. That's fair game. Phase lock loop, this is a synthesizer type example. We'll just leave that alone for now till the final. But this is a first order phase lock loop. These questions are very typical of what I'll expect you to be able to do. It could be that I'll take this exact problem and change the numbers up entirely. I mean, there's not a whole lot I can do with it, but so I would do something like that. I was thinking of something else that was in these solutions, but it's not here. It was in something I was looking at. My brain's in a blur because I'm looking at so many things. I will never, ever, ever, ever do this again. And it's not my fault. As far as I'm concerned, it's the administration that misled me into thinking I'd hand this class off. Trying to cram everything into a few days or weeks, a whole semester end is hard. I want you to be able to feel like you can be kicking back a little bit. I mean, you still have to keep working, but you don't have to do all the things that I've been trying to do crammed into a couple of weeks. You're going to just continue to flow it out. So when you don't come to class, you know, where is it?
That was on the 12th, right?
Yeah, let's just go back on this. We have this our calendar here. When you don't come to class on the 28th, be working on something. You got huge number of choices that you can work on. I want you to get the homeworks in on time. You can't, Slack will not lie to me if they're late and if they're way behind. I mean, I will decide when I get back, obviously. I will try to push solutions out if it's at all possible, because they're all queued up in my cloud account, and I have an iPad with me, so I can log into the web server. But who knows? I have no idea how well it will work from Europe. But stay on track with this. I'm trying to be like a parent saying, keep going. I'm giving you some guidance, basically. Don't let it all slide, because you will be in a world of hurt. And of course, you have other classes, right? So you got to keep pinging everything. Just don't drop this one into the trash can after the exam next week and say, I'm done. I don't have to worry about it until Dr. Wickard comes back. Keep being vigilant about it. We will be repeating this for the final in terms of the review. I think I have open book, open notes for the final, but I'm not positive. When I teach DSP, that's the way I do it. I don't remember how I did this. Probably I'll do it like that, though. I don't know. I don't have the answer to that. Fortunately, I don't have to figure that out right now, right? I have to figure it out on Tuesday morning when I come back, and then I have to be able to tell you when I'm going to write the exam. So 10:38. Questions? I realize your brain is loaded with a lot of things. It's not loaded with doing anything. I've been trying to get all this stuff done, but still, this is something that's very important to look at. And somebody who's not in class right now asked me, how do I find that thing? He didn't know where it was, and I said, look on the website. It's just right there. And one of the things I want to point out to you is because of the way the web server works, I sometimes, if I post something, it doesn't really change. If I rev a document, it will take sometimes hours for this WordPress web server to actually post it, make the change. I don't have a control over that. So sometimes what I do, if I want to make sure a document really gets in place, I will put up a new version of the document. I will add another digit to it. I'll say it's like _1 at the end. So why I'm saying that is, if you were to put this exact link in your browser, right now I have it as _1, and if I want to make sure it's up there, I will change the link. So the link will actually be _2. And the date always gets reflected immediately, but if I put a new version up, this thing will not always work for a matter of hours. It frustrates me to no end, and I haven't beat up on IT about it, but they'll probably say it's WordPress, we can't control it. They gave it to me. And I don't like that at all. I like the ability to push, which is why I have the ability to have the date code and time codes, which I insisted upon when they set me up with this. And they finally got that working on Mountain Daylight Time. It was UTC originally, which means it was over in Greenwich, England. So it was showing I was doing things in the middle of the night, when actually it was because it had a date code going wrong. Software, right? So many ways of making it not work right. I'm going up to lab, and I will be up there. I'm not feeling sicker like my wife is thinking I should, so I'm going to hang out for a while before I take off and do some more stuff. Nobody's got questions though, but you're not bored, right? Is anybody feeling bored? Good. I'm not feeling bored either, so we're in this together.